Saturn is an icon. There's nothing else like it in the solar system, and it's something even children recognize. But there's a distant object that astronomers call the Saturn Nebula, because from a distance it resembles the planet, with its pronounced ringed shape. The Saturn Nebula bears no relation to the planet, except in shape. It's about 5,000 light-years away, so in a small backyard telescope, it does resemble the planet. But when astronomers train large telescopes on it, the illusion falls apart. Scientists at Spain's Instituto de Astrofísica de Canarias (IAC) were part of a recent study of the Saturn Nebula. Their paper, called An Imaging Spectroscopic Survey of the Planetary Nebula in GC 7009 with MUSE, was published in the journal Astronomy and Astrophysics. It's the first detailed study of a galactic planetary nebula with a MUSE multi-unit spectral explorer integral field spectrograph on ESO's Very Large Telescope (VLT). The lead author of the study is Jeremy Walsh, researcher at the European Southern Observatory (ESO), home of the VLT. The Saturn Nebula is a planetary nebula, an unfortunate name for this type of object. Planetary nebulae have nothing to do with planets and everything to do with stars. A planetary nebula is actually a stellar remnant, a bright, shining corpse left over after a star runs out of fuel and dies. What's left is an intricate structure of clouds of different temperature gases, lit up by a white dwarf in the center. They're called planetary nebula when they were first seen through telescopes, because at a distance, they look similar to the gas giants in our own solar system. Unfortunately, the name has stuck, confusing the astro-curious ever since. The Saturn Nebula, or NGC 7009 as it's known, is one of the most complex planetary nebula out there, and that complexity makes it an intriguing object of study for astronomers and astrophysicists. Why wouldn't it be? Just look at it. The spectacular planetary nebula in GC 7009, or the Saturn Nebula, emerges from the darkness like a series of oddly shaped bubbles, lit up in glorious pinks and blues. This colorful image was captured by the powerful MUSE instrument on ESO's Very Large Telescope (VLT), as part of a study which mapped the dust inside a planetary nebula for the first time. Image credit, ESO, J. Walsh. This new study is the first time the MUSE instrument on the VLT has been used to study a galactic planetary nebula. Astronomers involved in the study say that MUSE has revealed unexpected complexity in the Saturn Nebula. The nebula itself consists of gas and dust expelled by a red giant star at the end of its life, lit up by the leftover white dwarf at its center. Astronomers know this because they can see the whole process played out in other stars throughout the sky at different stages of life. But what they don't know is the detail in the history of a planetary nebula's formation. And they don't like not knowing. The MUSE instrument on the VLT is ideal for work like this. This view shows how the MUSE instrument on ESO's Very Large Telescope gives a three-dimensional depiction of the Saturn Nebula. For each part of this spectacular nebula, the light has been split up into its component colors, revealing in detail the chemical and physical properties of each pixel. During the subsequent analysis, the astronomer can move through the data and study different views of the object at different wavelengths, just like tuning a television to different channels at different frequencies. Image credit, ESO, J. Walsh. MUSE has the powerful ability to sense the intensity of the light as a function of its color, or wavelength, in each of the pixels in its images. In a single image, MUSE can obtain 900,000 spectra of tiny patches of the sky. It can capture images of objects like the planetary nebula in 3 dimensions, and astronomers used all this information to reveal unexpected complexity in the Saturn Nebula. What they found was a series of structures, associated with different atoms and ions. The MUSE instrument at the European Southern Observatory's VLT. MUSE has given astronomers a detailed view of the Saturn Nebula. Image credit, ESO. The study revealed that these structures represent real differences in properties within the nebula, such as higher and lower density, as well as higher and lower temperatures, explains Jeremy Walsh, researcher at the European Southern Observatory, ESO, and first author of the study. Walsh reports one of the implications is that historical and simpler studies based on the morphological appearance of planetary nebulae seem to signal important links to the underlying conditions within the gas. The spectacular planetary nebula in GC 7009, or the Saturn Nebula, emerges from the darkness like a series of oddly shaped bubbles, lit up in glorious pinks and blues. This colorful image was captured by the powerful MUSE instrument on ESO's Very Large Telescope, VLT, as part of a study which mapped the dust inside a planetary nebula for the first time. This annotated version labels the features of this curious object. Image credit, ESO, J. Walsh. Using the power of the MUSE instrument and the VLT, the team behind the study revealed data showing that the gas inside this nebula is by no means uniform. The paper maps out gas and dust subformations within the nebula of 4 temperatures and 3 densities. Anna Monreale-Burrow, second author of the article and researcher at the IAC, remarked on the presence and distribution of hydrogen and helium in the Saturn Nebula. Hydrogen and helium are the 2 most plentiful elements in the universe, and their characteristics in the nebula are crucial to understanding the formation of the object and the death of the red giant that created it. Concerning hydrogen, Burrow said, the presence of dust within a nebula could also be deduced from the change in color between different emission lines of hydrogen, whose expected color can be determined by atomic theory. Our team found that the distribution of dust in the nebula is not uniform, but shows a drop at the rim of the inner gas shell. This result suggests sharp changes in the ejection of dust during the last death rattles of the solar-type star or, alternatively, of local dust formation and destruction. When it comes to helium, current nebula theory says that its distribution in a planetary nebula should be uniform. To test this, the authors used MUSE data to map the helium in the Saturn Nebula. They found variations that followed the shell morphology of the nebula. This implies that current methods of determining helium need improvement, or that the assumption that the abundance is uniform should be rejected, says Monreale-Burrow. Planetary nebula are fascinating objects. Their luminous, ghostly veils of gas and dust are irresistible to the eye. This is the first time that MUSE has been used to study a planetary nebula, and though the beauty of the object is a little mesmerizing, it's the underlying science that intrigues astronomers and astrophysicists. The authors of the paper admit that they are presenting only a limited amount of analysis in some respects. But their work shows that the MUSE instrument is full of potential. As they say in the conclusion of their paper, the observations demonstrate the huge potential of this instrument for advancing optical spectroscopic studies of extended emission nebulae.